Good afternoon, ladies and gentlemen. Welcome here at the Technical Forum at the group exhibit Hydrogen, Fuel Cells and Batteries. I welcome you here in the year of 2015 at the Hanover Fairground. I invite you all standing around to have a seat and have a drink. There's a lovely lady walking around serving you with complimentary drinks all on the house today. We are discussing topics regarding the projects from the FCH joint undertaking, a EU project together with a consortium that is helping the industry, especially in hydrogen and fuel cell, and also to have a lean carbon future. Our next speaker will present to you the topic about the fuel cell buses. He will give a snapshot on the CHIC project, and he'll also tell us about the next step. He will explain to us what the CHIC project is, and that is Director of Element Energy, Mr. Ben Madden.
Thanks very much. Is that okay? Thanks very much for having me and for inviting me to be here. It's always a great pleasure to come to Hanover. So I'm here, obviously I'm a Director at Element Energy, but the reason I'm talking to you is that we're the work package leaders for the dissemination work package for the CHIC project, which is Europe's largest hydrogen bus demonstration project. So what I'm going to do today is just give a little introduction to the project, the way it's constructed, give a quick snapshot of the overall status of the project, and then start trying to draw out some of the emerging results and lessons that have been learned to date. And then I'll finish with some remarks on what this is telling us about the future of the technology. So what is the CHIC project? Well, it's a deployment project based on 56 fuel cell buses from 6 different fuel cell bus manufacturers in 9 different cities. And when we talk about the project, we make a distinction between the phase 0 cities. Those are cities that had already achieved funding in advance of the project but wanted to join us to share data, and the so-called phase 1 cities who received funding from the FCHJU to buy new buses and refueling infrastructure. So the phase 0 cities are Hamburg, who have just recently taken delivery of 2 Solaris fuel cell buses and have been operating 4 Daimler EvoBus fuel cell buses for about 2 years. Hamburg, who've been operating 2 double articulated APTS buses for about 3 years and have recently taken delivery of 2 Van Hool buses. And then Whistler in Canada, who took 20 fuel cell buses in time for the Winter Olympic Games in 2010. And I'll talk a little bit about the phase 1 buses in a second. Just in terms of the deployment timescales, the project began in 2009 with the introduction of the 20 Whistler buses in time for the Winter Olympic Games, and then grew through time to the point that last year we had about 52 buses on the road at any given point. That's dropped slightly as we come towards the end of the project because the demonstration phase in Whistler has ended. That's been slightly offset by new deployments of Van Hool and Solaris buses in Cologne and also in Hamburg. And it's important to note that this project shouldn't be seen in isolation. This is the first of a number of large fuel cell bus demonstration projects which have been implemented over recent years. There's the High Velocity Project, High Transit, and 3Motion project, and then there are also a series of smaller national initiatives, particularly here in Germany. The effect of all of this is that by the end of next year, we would expect 83 fuel cell buses to be in operation around Europe. And you can see that that really is already a move from a sort of a demonstration mode to the beginnings of an early commercial deployment, albeit with significant state support. I promised a few words on the phase 1 cities. So 3 of the cities are using Daimler EvoBus buses. There are 3 buses operating in Milan, 5 in Aargau in Switzerland, and 5 in Bolzano in northern Italy, up in mountainous terrain. In Oslo, they're using 5 Van Hool buses, which are the same buses that have just been deployed in Cologne. And then in London, we're using the Wrightbus vehicle, which is also in which they are collaborating very closely with the fuel cell manufacturer Ballard. And of course, these vehicles also need somewhere to refuel. In the phase 1 cities, 4 of the sites are using electrolyzers, using renewable hydrogen. And the only exception is in London, where hydrogen is being delivered using a liquid tanker originally, and now increasingly just using large, new high-pressure tube trailers. In the phase 0 cities, hydrogen for Cologne is coming from a nearby industrial park where the hydrogen would have otherwise been wasted. It was essentially a byproduct from other chemical processes. In Hamburg, the processes electrolysis, on-site electrolysis. And in Whistler, hydrogen is transported in liquid form from Quebec, where hydropower is used to generate the hydrogen, and that's about 4,000 kilometers away. But even still, the overall carbon footprint of the hydrogen is remarkably low. So that's just a brief introduction to the technology. In terms of the overall status and where are we, taken as a whole, the project has, the buses on the project have traveled over 7.6 million kilometers in passenger carrying operation. And the phase 1 cities themselves have traveled over 2.3 million kilometers themselves. So we're well on the way to achieving the high-level project target for the phase 1 cities of 2.75 million kilometers. That will be comfortably met. The fuel cell stacks in the phase 1 cities have operated for over 150,000 hours, and we've used more than 220 tons of hydrogen, and then taken as a whole across the project more than 1,000 tons of hydrogen. So we're starting to assemble a really valuable, large-scale data set of real-world operation for these buses, from which we can start to get a true sense of where the technology is and what's going to be needed to put it into mainstream use. And what I hope to do is just take a few of the main results from the project. So the first main result is probably easiest to overlook, which is that these buses are acting as a like-for-like replacement for diesel buses on conventional bus routes. The previous trial, which was called CUTE and then High Fleet CUTE, was constrained by the fact that the buses could only travel about 12 hours a day and a maximum of well less than 200 kilometers in any given day. That meant they couldn't fulfill the daily needs of a typical bus. Across all of the cities in this project, the buses are going out at the start of the day, coming back at the same time as a diesel bus at the end of the day, and providing exactly the same service with no compromise to the operational flexibility of the operators. So that's a major advance and means that the technology is in principle ready to be a direct and easy replacement for the existing diesel bus fleets that we use in our cities. The other major advance has been around fuel economy. Again, on the High Fleet CUTE project, where the buses were in a non-hybridized drivetrain, we saw fuel consumption of between 18 kilograms per 100 kilometers all the way up to 29 kilograms of hydrogen per 100 kilometers. All of the buses in the CHIC project have exceeded the target of 13 kilograms of hydrogen per 100 kilometers. But perhaps more significantly, the 12-meter buses within the phase 1 cities have achieved an average fuel economy of around about 8 kilograms of hydrogen per 100 kilometers. So when we compare that to the previous generation, we've more than halved the fuel consumption, which is a major advance for a single generation. And that's been achieved by hybridizing the drivetrain, so adding a battery and allowing regeneration of braking energy, but also allowing the fuel cell to operate closer to its set point. So a major and significant advance. Turning to the fueling stations, the major problem in the High Fleet CUTE project was filling stations. We typically saw refueling times of 30 minutes to an hour for a bus, which is just not acceptable for diesel bus operators who usually operate their buses in a 3-minute window. On this project, all of the stations have exceeded their refueling targets, and we typically see refueling of about 7 minutes for a bus from empty. So that's pretty close to the required level to match a diesel bus. And all of this has been done with relatively high availability. So in a number of the sites, we've exceeded the project goal of 98% reliability comfortably. I think in London there have been 3 days in 4 years where there's been any kind of outage which has affected service. Those sites which haven't achieved the required level of reliability, generally it's been because a single component has failed and then taken a long time to fix. And that's a problem which you would expect to see resolved in a more mature supply chain. So what we see is stations which are working for fueling 5s and 10s of buses, but it's fair to say that the operators on the project are slightly anxious about what happens when you get to 100 buses, the kind of number of buses that are operated out of a typical depot. There are problems then around, is the technology ready to push tons of hydrogen into buses in any given day? And there are also questions around reliability. 98% is all very well for a demonstration project, but if your entire public transport system is relying on buses, you need to be hitting effectively 100% reliability day in, day out. So there's still a little bit of work to be done there. And then perhaps the most challenging result on the project has related to the availability of the buses. This graph, I hope you can see it, just shows these yellow bars are the average monthly availability of the buses, which means their readiness for service through time. As we've gone through the project, this is time, you probably can't read that, from January 12 all the way through to a couple of months ago this year. And what you can see is that at the start of the project, all of the buses in every single city were falling well below the availability expectation, which was to hit 85% overall availability. So really falling very far short. And you can imagine that at the start, that led to great complaints and fighting between bus operators and manufacturers, the operators feeling that they weren't getting the technology that they'd originally been promised. That shouting eventually gave way to some reflection on the reasons for this poor availability. And generally the conclusion has been that the reliability that we've seen is probably what could be realistically expected from this first serious deployment of fuel cell hybrid drivetrains around the world. There are two main reasons for the poor reliability. The first relates to the maturity of the supply chain. So when a part breaks on a fuel cell bus, it takes days or weeks to fix. Whereas on a diesel bus, you would already have a part in stock at the operator site and it would take no time at all to fix. The other problem on maturity is that there's typically maybe one or two people in any given depot who can maintain a bus. So in some sites, you can actually see when key maintenance people go on holiday, the availability of the buses dips, which is a bit ridiculous for a technology in the mainstream and wouldn't be a problem with scale. So these are both problems that can be resolved fairly simply by just increasing the amount of buses that are in operation and the overall scale within the supply chain. The other problem has been a teething problem. So a number of the components have had issues. So that means the DC to DC converters on the Daimler buses, the air compressors on the Van Hool buses, and also generally the software that's being used to control the hybrid drive system. There's also been issues around the way the maintenance regimes have worked in terms of basically the maintenance staff learning to fix these buses through time. So what you can see is a gradual improvement through time as people learned to fix the buses better. And then we had a phase at the start of this year where we decided to do a major upgrade program on all of the buses to try to fix these component level problems. And you can see that led initially to a dip in availability here as the buses were taken off the road to be fixed. But since then, that's given way to a phase where the reliability or the availability of the buses over the last 6 months has pretty much consistently hit the 85% target level for the project. So it's a really encouraging result, and actually might be turning what started out as a negative story into a really positive one, where we started with a poor reliability at the start of the project and disappointing results, but probably consistent with the technology readiness level for a technology that was being deployed in this form for the first time. Improving through time through a combination of learning and then improvements in components to the point that we're now hitting 85%, which is the project target, and the operators expect that level to be achieved for the remaining 18 months of the project. So we're actually starting to see the CHIC project telling the story of the technology having matured to the point that it can now be relied on as a reliable option. I think it's a little too early to call that, but it's the beginnings of very encouraging results. We've also done a series of socioeconomic, techno-economic and environmental studies, which I don't have time to go into today. Suffice to say that the surveys suggest that passengers and bus drivers are really happy with the technology when they realize they're driving a hydrogen bus at all. Perhaps the only issue for them has been around the greenness of the hydrogen. Their support for this technology and their enthusiasm for it is contingent on them believing that the hydrogen is sufficiently green. And that means that's a challenge for the industry to A, provide green hydrogen, but B, perhaps more importantly, to sell the green hydrogen story to customers and bus drivers alike. The environmental analysis is as you would expect. It demonstrates clearly the buses offer zero emissions at the point of use, but also on a whole life basis, the airborne pollutant emissions are negligible and massive savings over conventional diesel buses. On CO2, when the hydrogen is generated from a clean fuel, from a clean source, clearly the carbon emissions are essentially negligible. But perhaps the more interesting result is that even when hydrogen is generated from natural gas, the carbon savings in the early calculations suggest about a 50% CO2 saving compared with a conventional diesel bus. So that's already a significant saving, even using today's dominant hydrogen production method. So I'll just wrap up with a few conclusions about what this means for where the sector is going. Taken as a whole, the CHIC project is starting to show that hydrogen buses can offer a genuine, like-for-like drop-in replacement for diesel buses with absolutely no compromise for the operators. That's a different story to the story with electric buses where there are range limitations associated with batteries or a requirement to connect cables in the street. And they can do this with zero emissions at the point of use, and with a medium term and actually a relatively short term trajectory to the full decarbonisation of public transport. And this is all in a way that bus drivers, passengers really like. They enjoy using the buses and they want to see more of them on their streets. So these should be appealing to politicians, and they should have, and the CHIC project as a whole is showing that the technology has the potential to be transformative for public transport. There are challenges, and there are three, I think, that prevent us from running into a phase of commercialization. The first one is around availability, and I've already really mentioned that. We need the existing programs, the CHIC program, and then the future programs that are about to start to demonstrate that you can hit the 85% level of reliability on a consistent basis. And then further increases towards the 90 and 95% that you might expect from a diesel bus will then be delivered with increases in scale in the overall supply chain. The second point is around cost. Over the course of the project, the CHIC project, the cost of fuel cell buses, has more than halved. So when we started, a fuel cell bus cost between 1.5 and 1.8 million euros. The last bus quote I saw was at 850,000 euros, and people are already starting to talk about prices as low as 650,000 euros for buses procured next year. So that's a pretty significant advance. But for the technology to really work, we're going to need another halving again in it to be properly competitive with other vehicles. And the good news is that the FCHJU is taking action on this. They've already brought together a so-called commercialization strategy group, which is looking to bring together bus operators and end users with manufacturers to make an order of a sufficient size that the bus manufacturers can start to really drive their prices down. So that's good news. And then the third point, which is perhaps not as important as the other two, relates to refueling. I already mentioned that we don't really have engineering solutions at a depot scale that understand the level of reliability that will be required and the technology that will be required for the tons of hydrogen a day that would be required to refuel buses on a depot scale. And again, there's good news here, which is that the FCHJU is about to launch a study to look at, I think it's 13 different depots, and come up with detailed engineering studies to understand what a 100-bus refueling solution would look like, how that would interact with the logistics of the bus depot, etc. Hopefully thereby removing one of the major risks to starting to back this technology as a mainstream public transport operation. So I think overall the CHIC project has taken some time to get going, but is starting to show really encouraging results about the potential for this technology to act as a true replacement for diesel buses and be really transformative for the way we do our public transport. Many thanks.
Thank you very much also from my side for this very interesting look on the CHIC project, on fuel cell buses. And are there any questions from the audience?
Thanks for the presentation, very, very interesting. You mentioned, you touched upon a very key issue, which I think is the footprint of hydrogen and how important it is to show the end user that we're effectively using green hydrogen. So I was wondering what was the reasons for the selection of liquid hydrogen supply for London, for instance?
Yeah. Well, I suppose the first point I would make is that finding came after the decision. In London, as you can imagine, bus depot space is really constrained. So there are significant footprint advantages to moving to a liquid supply. The other reason was around the on-site, so this is in 2009. So electrolyzers at that point were very expensive, and I think a different decision might have been made today. The main on-site option that was being discussed then was reformers. So it was essentially a compromise between reformers or on-site delivery. So the environmental argument was less strong anyway, but also reformers just don't have the operational flexibility to cope with the variability of bus operation. 4 buses go off the road, the reformers can't modulate as well as they would need to be able to deal with that change in supply. So it was a combination of operational flexibility and footprint, and the fact that, frankly, electrolyzers weren't where they are today.
Thank you. I do have a question before I accept more questions from the audience. I do live in the city of Hamburg, and I know the fuel cell buses. I've seen them, happy when I see them. I know the station. I live very close to it. Now, my question is, what estimation do you have in which year would the fuel cell buses be so integrated in the economy that they are economy of scale? When is the scale production?
So I mean, again, it's slightly future gazing, so it's anybody's guess. But the plan is, and the way the FCHJU is thinking about this at the moment, would be to try to have effectively a subsidized program of hundreds of buses in the period 2015 to 2020.
Okay.
So it's still a phase of improving the technology, progressively bringing costs down. The idea is that that has achieved sufficient economies of scale that at the end of that, so from 2020, you can start to make a commercial case for the deployment of buses. The other good news about Hamburg is that I think your mayor has a policy that by 2020, all new buses need to be zero emission. So it'll either be electric or fuel cell buses by that stage.
Yeah. That is correct. Are there any more questions from the audience? That is not the case. Well, unfortunately, we have to say goodbye then to Mr. Van Madden. It was a pleasure to have you here and have this really interesting look on the fuel cell project, the bus project. And once again, I would like to thank you. Also, thank you from the audience. Thank you from all our online guests. Thank you for this wonderful presentation.
Thank you.
We are already at the end of our program here in the Technical Forum. I am thankful for everyone who has participated in the presentation, in the talks. It has been a very interesting day regarding the off-grid fuel cell applications. Tomorrow we'll continue with our program. We'll start at 11 o'clock and then we'll talk about the influence of ceramic powder quality on processing and SOFC performance. I'd like to welcome you to stay here for a little bit, enjoy your coffee. Other than that, please relax and pardon? Yes. Okay. Thank you. Thank you very much and goodbye.